welcome to the lecture of this finite volume method. So, once the stencil definition is over, we can move to the. So, if you keep this picture in mind, this is how we have it. This is my cell C, this is my E or AC, this is my north, so north face, this is my west face, so W, this is my south, south face, okay. And the distance between this is east, distance between this is delta x E, distance between this is delta x W, distance between these two is delta y south, and distance between this is delta y north. So, this is a small information, if you keep in mind, then we can. So, our equation is del dot J phi is q, okay, where your diffusion flux is defined as minus gamma delta phi, okay. So, as we have done that, you do the integration or volume integration and then convert to surface integral to get back a algebraic equation. So, that we have already done. So, if you follow the same procedure, essentially doing the integration and all this will turn out to be the summation of f over all the faces minus gamma delta phi of f dot SF equals to q v c. So, we are writing for V c is the volume of element C and Q c is the source or sink for element C, okay. So, that is what it does. You get this algebraic system, okay. So, if you expand this one, now you expand this one, once you expand this one, this will now essentially this is written for this element C here, and once you expand that, it will go over these 4 surfaces. So, it is a 2D element, so the loop goes over, loops over 4 faces, and the faces are east, west, north, south, and that is why it is very, very important to keep track of this notation east, west, north, south. So, if I expand it, it will be now written minus gamma del phi at east face dot is plus minus gamma del phi west face dot west vector minus del phi north dot Sn plus minus gamma del phi south dot Ss equals to Qc Vc. So, that is my expanded equation which is turning out to be. Now, this grid is uniform, number 1, Cartesian, Okay. So, the surface vector are normal to the respective faces. Okay. This is very, very important. If that does not happen, then we cannot straight away, we have already seen we cannot, if they are not collinear or they are some sort of a off the center connections, then we cannot straight calculate the surface vectors. So, having said that, we can estimate AC. AC would be nothing but the surface vector which is delta y positive east dot I. So, this should be essentially magnitude of AC I. So, one can write AC I. So, the normal vector is here SE, which would be this distance into the unit depth. So, that is what it does. Similarly, you write for SW, which is minus delta y W I. So, this should be minus SW I or SW I. And why does this minus sign come here? Because if you assume this is the local coordinate system, this goes in a positive I and this goes in positive j. So, this is my positive direction, this becomes negative direction. Okay. Sn would be delta x positive n dot I, which is essentially n dot j Sn j, and similarly S would be minus delta x S j, which is a S j. So, here you get all your surface vector definition. Once you get that surface vector definition, you can calculate all these individual surface fluxes, the diffusion fluxes. First, let us look at the east face. So, if you look at the east face, so that is essentially your J E dot S. So, this should be minus gamma del phi E equals to E dot S E. So, this is the term essentially. Now, this term if you expand, now this would be gamma E S E del phi by del x I plus del phi by del y j dot product with I, because my AC is essentially AC I. So, this is the dot product with I, and what you get back here, it is a dot product of I. So, you get back with this term only, minus gamma E AC del phi by del x E. Okay. So, that is my east phase diffusion flux. if you look at it, now we got a expression. We will continue this notation for all the phases like gamma E, gamma W, gamma N and gamma S, just to represent that if there is no non-homogeneity, then they would be equal. If there is a there is a homogeneity, they would be equal. If they are not homogeneous, then they could be different. And the discretization technique or the numerics essentially takes into account the non-homogeneous contribution of the diffusion term. So, that is what we will retain this suffix of individual phases. Now, once you obtain that, so if you now write the diffusion flux at the east phase, which is total flux at east phase, which is the flux C phi C plus flux F E phi F plus flux B E. So, flux C, flux B E and F E, these are essentially coefficients of phi variation between C and F, that means any neighboring element. So, these are the coefficients. Now, if you assume the linear variation, let us say the phi variation is linear, then you can have the system like this: C east, this is east phase, this is the distance delta x E, and this is the variation, and the linear variation will do the job. So, this would be phi C and this would be phi E, and the slope is del phi by del x. So, this is the slope of that linear variation. So, that is the profile would be the interpolation slope of these two. So, what I can write del phi by del x E with the linear variation phi E minus phi C divided by del x E. Now, this expression, if you replace in this particular equation, so combine these two, what you get is that total flux is minus gamma E delta y E, which we have, this is gamma E A C del phi by del x. So, gamma E delta y E phi E minus phi C divided by del x E. So, if I rewrite that, this should be gamma E delta y e by delta x c phi c minus phi e. So, this negative sign is taken into account, which is also equivalent to my expression flux C e phi c flux F e phi f flux V e. So, this would be, you can write this one flux E here. So, if you take the mapping of the coefficients, you get here, before that you define this particular system, let us say d E equals to delta y E by del x e. So, then if you map the coefficients for phi c and phi e, you get flux C e equals to gamma e d e. Similarly, flux F e equals to minus gamma e d e, and the third one, the flux B e is 0. So, this is what you get as the coefficient. So, once you get that, then you got your these things. Now, when you move to the waste phase, we can similarly find out that flux, the total flux at the waste phase is minus gamma del phi W dot S W. So, which will turn out to be minus gamma W S W del phi by del x I del phi by del y j dot minus I. So, this is as per our definition of S W. Okay. So, S W is minus I. So, if you do this, this would be gamma W S W by del phi by del x W, okay, and which can be again written that. So, I can write the total flux T W equals to gamma W S W del phi by del x W, which is nothing but gamma W S W phi c minus phi W divided by del x W, and the coefficients would be flux C W phi c flux F W phi W plus flux V W. If you match the coefficients from these two equations, then you get flux C W equals to gamma W d f d W flux F W equals to minus gamma W d W. and flux Vw equals to 0. So, these are the coefficients that you get, and the dW definition is similar to our dE definitions, which would be like where dW is my delta y W by del x W, which one can think about magnitude of SW divided by dCW, which is SW by dCW. So, that is our definition of. So, similarly, we could write for SDE, that dE we had definition of del YE by del XE, which is magnitude of AC divided by DCE, which is AC by DCE. So, we got the surface of east and west. Now, you have two more surfaces which are left, the north and south. So, you can get it in similar fashion. We have all the required information which is available. So, if I put this together, the flux T n, the total flux would be flux C n phi n, or flux C n phi C, flux F n phi n plus flux V n. Okay. And the south would be flux T s, the total flux would be flux C s phi C, flux F s phi s plus flux V s. Okay. So, this is the total flux definition, and once you do the mapping for each case, you get, for this case you get where flux C n would be gamma n d n, flux F n would be minus gamma n d n, and flux V n would be 0. And similarly, for this case we get flux C s is gamma s d s, flux F s equals to minus gamma s d s, and flux V s equals to 0. So, you got all these coefficients, and where your d n would be magnitude of S n divided by d C n, which is nothing but your delta x n by delta y n, which is S n by d C n. Similarly, you get d s definition, which would be S s divided by d C s, which is delta x s by delta y s, S s by d C s. So, you got all these coefficients, and Now, if you put them together in the final equation that you had, basically the equation of this, that you had minus gamma del phi is dot AC plus minus gamma del phi W dot SW plus minus gamma del phi N dot Sn plus minus gamma del phi S dot Ss equals to QC Vc. So, if you put everything together in this particular equation, now whatever we have now obtained, if you put them together, so what you get? You get an equation AC phi C plus AE phi E plus AW phi W plus AN phi N plus AS phi S equals to BC. So, this is the algebraic equation that you get, or the linear equation, and the coefficients that you can calculate, and we will see how to calculate that in the follow up lecture. Thank you.